right, everyone. Jamelis again. Let's talk. Let's talk about Physics 209, calculus-based treatment. Physics 209, calculus-based treatment, the Katz book, first edition. That's what we've been doing. Pretty much whenever we say the 209 these days on these videos, we're talking about the Katz book. This is going to be chapter 13, the following problems. 9, 33, 53, 54, 70, 71. So let's see how that proceeds. Looking at problem number 9. Problem number 9 from chapter 13. It says a solid sphere of mass capital M and radius capital R is rotating around an axis that is tangent to the sphere. What is the rotational inertia of the sphere in this scenario in terms of M and R? Well, okay. Let's kind of kill a few birds with one stone, so to speak. As we look at this stuff, you guys, for number 9, for example, we know a lot of stuff. They got this thing called the parallel axis theorem. I have a proof of the parallel axis theorem. I have 2 proofs in there for you in the notes in Canvas. One of the proofs is from one of the textbooks of some time ago. You probably don't readily have access to it. We actually proved the parallel axis theorem by means of conservation of energy considerations. There is another one where I use, I more or less did this using vector analysis considerations. I'm sure I was not the first person to do that, but I can't remember seeing that anywhere else, but I've not looked everywhere else either, right? So, but I have a proof for you where I use conservation of energy considerations from another book, and I also have one that I kind of sat down and looked at a little bit using vector analysis. So that's both of those are in Canvas where they talk about the parallel axis theorem. The parallel axis theorem says the moment of inertia of something is equal to the moment of inertia of that something about its center of mass plus the mass of the object h units away from the center of mass of the object. If you're talking about something right here, the moment of inertia of something about its center of mass is ICM. If you take the object and move it over here, where it's h units away from, and you're still going to rotate it about here. You're not going to rotate it about here. So let me, maybe to avoid any confusion, get rid of that. And you're going to have this thing go around here, and you no longer have so you picked it up and you put it over here, so it's no longer there, but you are going around this axis. This axis is right here, around which you are having the rotation occur, and this guy's like this right here. You would treat it as though there was something right here, which is the ICM of this guy. If this were the moment, if this were the place where the rotation was taking place, if this right here were the place where the rotation was taking place, then it'd be the moment of inertia about the center of mass, going right through the center of mass of this thing. But if you take this guy and actually make the axis h units away, then this moment of inertia indeed becomes, it would be ICM right here, but if you move it over here, this I becomes, as we just said, the moment of inertia as though we were talking about going through the center of mass and rotating through the center of mass, plus the mass of the object times h squared. So that's kind of the argument here with that. So that's all they're kind of asking, guys. They're not asking anything too fancy. But again, the moment of inertia of something that's away from rotating about its center of mass. It's away from, so to speak, away from rotating about its center of mass. It's h units away from rotating about its center of mass. Then the new moment of inertia becomes, add this to the moment of inertia as though it's going through the center of mass. And again, there's two proofs of that that are available for you on Canvas if you want to look at it. Oftentimes, we're not really doing proofs, guys, but like I said, for your personal enrichment, it's not a bad way to go. If you look at it by the parallel axis theorem, we're taking, I of the sphere, ICM of a sphere, as though you were going through the center of mass, if we look it up, is 2/5 mr squared. At a distance, h away, if it was just a point mass, it would be mh squared. So you're basically just adding the two of those, as we have said. This is the third time you're seeing it here, guys, but as we said, the repetition is the mother of learning oftentimes. So you got that. What does that mean? Well, they decided to put this thing, here it is. They decided to go away from the center of mass and go right to the edge. In other words, have the center of mass be capital R units away. And here's where it would have been, and you went capital R units away. So how does that play out? The way that plays out is ICM, center of mass, mh squared, that's m, the h is an r. That's the distance right here, you guys. That's r. So what we have here is, this is 5 over 5 times mr squared. Well, it's 1 plus 2/5 is 1 2/5. That's 7/5 mr squared. And that's all that they're talking about regarding number 7. Let's go to 33. Let's see what we can say here, guys. For 33, there is a lot being said here. Let's see what we can say. A spring with spring constant 25 newtons per meters is compressed a distance of 7 centimeters by a ball with a mass of 202.5 grams. The ball is then released and rolls without slipping along a horizontal surface, leaving the spring at a point A. The process is repeated using a block instead, with a mass identical to that of the ball. The block compresses the spring by 7 centimeters, just like the ball did, and is also released, leaving the spring at point A. Assume that the ball rolls, but ignore other effects of friction. What is the speed of the ball at point B? What is the speed of the block at point B? Without slipping, they've got to be talking about, so the ball rolls without the effects of friction. I think we got to assume that there's no friction. There's no effects of friction that are going to affect anybody, the ball or the block. And they want to see how they go. Now, people, your common sense would say, hey, wait a minute, man. You've got the spring. The spring is, the spring is whatever it is, and it doesn't change in both scenarios. Whether the ball or the block, we're using the same spring. We're using the same surface, the whole thing here. The ball is going to be ejected out of there, and then the ball is going to roll without slipping. But it is going to roll. If it didn't roll, I'll tell you something right now, right off the bat. If it was a frictionless surface, let's say, there's a lot we're supposed to assume here, and there's a good amount we're not being told. But that's, I mean, they can't, they're limited in how much they can say, guys. Otherwise, every single problem would be this long. So I get it. You know, we got to use Occam's razor again sometimes as well. Though that can get confusing sometimes as well. You want to know specifically what you're being asked because a lot could ride on a problem if it's an exam or something, right? So anyway, that's neither here nor there. For the homework problems and for what we're doing, we're not going to have any issues with the block. The block ain't going to be rolling, and it's not going to be dealing with friction because they didn't tell us anything about friction. So there's no friction associated with the block. So it's just going to go and it's not going to roll. The ball is not going to have any frictional considerations associated with it either for our purposes. However, it is going to roll. If the ball did not roll at all, and the block, of course, does not roll, they would both go the exact same distance if the same compression was going on for both of those. Well, that's not happened here because the ball is rolling. The fact that the ball's rolling, the fact that it's rolling, something happens. I mean, something happens that's, there's the rolling consideration associated with kinetic energy, and there's the actual translational consideration associated with kinetic energy. So in a sense, the energy of the system kind of gets partitioned in some sense in two different places to some degree or another. There's a lot they can tell you here, I guess, but let's talk about, I mean, they talk about the sphere and they talk about the block. I got this in the notes. This is kind of operative everywhere. 25 newtons per meter. X is equal to delta X. That's kind of up to you which one you want to use. That's 7 centimeters. To be in agreement with everything else, 7 centimeters is 7 meters. 7 centimeters is 0.07 meters. Okay, when you're doing all this. M sub s is m of the sphere. M sub b is m of the block. They are telling us, well, I guess what the heck. Let's say m, generically written like that, is the same as m sub s, is the same as m sub b, is equal to 202.5 grams. All right, there's a lot of symmetry in a sense in this whole situation. So let's go to let's look at this and then go to the sphere and kind of have this. This is kind of our database from which we're working, you guys. Let's see what they want to do here. Let's go with the sphere and figure out what's going on here, and we'll figure out what's happening. They're saying that the I moment of inertia associated with the sphere. We don't worry about the moment of inertia of the block. There is a moment of inertia associated with the block depending upon the orientation of how you're going to pick something up, or how you're going to move something, or how you're going to spin something. This thing's not spinning at all. In no way is this thing spinning. It's kind of staying as is. So there's no rotational inertia that has to be considered. It's certainly there depending upon your reference frame, but it's not something that we need to worry about. So I is equal to I equals I sphere equals 2/5 mr squared. Yeah, that's we've already taught. In just the previous problem number 9, we talked about that. That's something we can look up. We can also derive this. I do have derivations of this as well. Do we need to know any of these derivations I'm putting forward? Later on, I'm going to talk about the Doppler effect that's going to be derived. I'm going to derive a whole bunch of stuff for you guys, and I'm going to have it on Canvas for you. Typically, you got to know how to use the stuff more than you have to know how to derive it. But for your personal enrichment, the derivations are there. Okay. We know that V is equal omega times R, depending on how this thing's spinning. We are told it is spinning. We are told that, well, we are told or know initial potential energy of a system plus the kinetic energy of a system initially. Initial potential and kinetic energy summed together will give you the final potential energy and kinetic energy summed together. Potential energy initial is 0. Forgive me, no. It's all potential energy in the beginning because the spring's been compressed. The initial kinetic energy is 0, forgive me. And at the end, there's no potential energy. So what are we talking about? There it is. Yeah, I mean, let's see what we got here. Potential energy initial equals kinetic energy final. What is the potential energy initial? It is 1/2 kx squared, and that's going to equal to the translational kinetic energy, plus you have to account for the fact that there's rotational kinetic energy going on. We've already derived 1/2 I omega squared. We already talked about that. Didn't we say V was equal to this? V equals omega R. What's I? They already told us I was 2/5 mr squared, omega squared on the outside of all that. Let's see what we got here, guys. You know, I don't know. Let's not make too big a deal out of this, but these right here, you know, M is also equal to capital M. Let me throw that in there. You see different things written different places. The way they give moments of inertia in the book, I think they got capital R's in there and they got capital M's in there. So let's see what we want to say about that. All right. What we have, there's a lot we have actually. Let's keep going, I guess. This is 1/2 capital M. Can write this a whole bunch of ways actually. Omega squared R squared. This is 1/2 of 2/5. That's 1/5. M R squared omega squared, or omega squared R squared. It doesn't really matter a lot. The big thing is that you get it. Guys, that term or this product and that product are identical. 1/5 the product plus 1/2 the same product is 1/2 times 1/5. And if you do the addition, 1/2 is 5/10. 1/2 is 5/10, and this is 2/10. It's going to be 7/10. 7/10 capital M omega squared R squared equals 1/2 That's fine. I guess they want, at the end of the day, you guys, they want you to find what V is. Now look, guys, you can kind of get yourself out of the woods a little bit here. You got to go back and forth. You got to be pretty slick about it. V is omega times R. V squared is omega squared R squared. So this guy right here is v squared. Omega squared r squared is v squared. Let's solve for v. Well, let's solve for v squared first. This is v squared. We've got 1/2 kx squared 7/10 mv squared multiplied by 10 and divide, multiply by 10 and divide by 7 on each side, and then also divide by capital M, and let's see what we got. We got v squared, so multiply by 10, a half time, you multiply by 10 on each side, half of 10 is 5, divide by 7, that's 7, divide by capital M, that's capital M, here's k, here's x squared, looks about right to me, square root both sides, square root of x squared is just x. That's it. I mean, that's where we're going to go. That's where we're going to go to get this. Well, what's what? What's what is this? 5 is 5. K, let's see, what did we say K was? K was 25 newtons per meter. Make sure all the units are green now, right? 5 is 5. 5 is 5. K is 25 newtons per meter. 7 is 7. M is 0.2025 kilograms. X is 7 centimeters, which is 0.07 meters. Go for it. 5 times 25 over the product, 7 times 0.2025, square root all that, then multiply it by 0.07. Well, okay, I mean, you got all the stuff there. You put all the stuff in there. We got 33A is 0.66 0.66 meters per second. That's the essential argument in a problem like this. And now when they throw the block at you, they didn't mention friction, so we're going to assume there's no friction with the block. There's no rotation either. Is that guaranteed? No, I mean, it could have been rotating sideways. And we got to deal with the moment of inertia there. They didn't really go into that. We use Occam's razor at that point. We make some valid assumptions and figure out where we're going to go. So if that's the case, let's see what we can say. All right, well, now what? I mean, what about that block? I mean, they said that there's a lot of similarities here. Well, the block's not rotating. So for 33B, the block's not rotating. So we're not really, it's a little bit different of a dynamic here, guys. We've got, and so similar as well. I mean, there's a lot here that should not be very shocking. It should be stuff we've already seen. It's just now in the part B of the problem. It's all potential energy initially. When you compress that thing, there's no kinetic energy initially. At the end, it's all kinetic energy, and there's no final potential energy. This is starting to look familiar. Starting to look familiar, guys. Here we go again. Kinetic energy is only translational kinetic energy. That's it. From here, you will solve. My gut tells me this block on a frictionless surface will move faster than the sphere of equal mass that is rotating. Because of the rotation, energy considerations, the energy of the system goes to two different places. To what degree, we can talk about that some other time. But what's going on here? How's this working? Well, there's rotational kinetic, there's different circumstances where that can be talked about. That's its own story. But there is translational kinetic energy and there's rotational kinetic energy. So the translational kinetic energy suffers as a result of there having to be a rotation as well. The energy's got to be accounted for. And if there is rotation, then that's part of the energy considerations in addition to translational kinetic energy. That was part A. We got a number, the 0.66 meters per second, given the fact that there was rotation as well. I got a feeling it's going to be more than 0.66 meters per second on this one. Let's go for it. You can see already the way this is playing out. Let's solve for v squared. Let's solve for v. V squared is going to be, once you multiply by 2 on each side, kx squared equals mv squared. Divide by m. You got x squared right here. Square root both sides. Okay, here goes. This is 25. This is 0.2025. This is 0.07. Take the 25 and divide it by 0.2025. Get an answer, square root it, then multiply by 0.07. We did not have to worry about the considerations of rotation. And that's B. Let's go to 53. One second, please, guys. Just want to, we're all in agreement here on some of the stuff I'm about to do later on. Let's go to 53. We'll kind of take it from there, I guess. So for 53, they're saying two children. For 53, two children, mass 30 kilograms each, stands opposite each other on the edge of a merry-go-round. The merry-go-round, which is a mass of 1.8 times 10 to the 2 kilograms, which is just 180 kilograms, you guys, and a radius of 1.5 meters, is spinning at a constant rate of 0.5 revolutions per second. Treat the two children and the merry-go-round as a system. A, B, C. How does it go? Here's A. Calculate the angular momentum of the system, treating each child as a particle. It'd be different if you weren't treating each child. You're treating each child's mass as though the mass is a particle, rather than the bulky situation of, what I am, what any other human being is. We're not just a particle. There's outward direction and stuff. So that would there's a moment of inertia to be considered. Even there, and the parallel axis theorem would be called into play. They're basically signaling to you, don't bring the parallel axis theorem in here. You don't have to. We're going to make it a little bit easier for you. So, calculate the angular momentum of the system. Treat each child as a particle. That's A. B. Calculate the total kinetic energy of the system. C. Both children walk half the distance toward the center of the merry-go-round. Calculate the final angular speed of the system. The kids are both going to walk. Each one is going to walk half the distance toward the center. My gut tells me if I was a figure skater and I have my arms around out and I'm spinning, when I bring my arms closer to my center of mass, I'm going to rotate faster. So I got a feeling this is going to rotate faster, you guys. Okay, let's take a look and see how they're doing this. And again, the notes are there for you on Canvas as well, as I'm saying this right now. Let's take a look at it. Okay, guys. Okay, I mean, there's a good amount being asked, but not too, it's all right, it's reasonable. Let's see what we got. Basically, what I'm saying is here, they want us to model the merry-go-round as a disk. So the merry-go-round itself, I mean, the assumption being made here, it's not a sphere, and it's not something where there's a point particle on the edge of an infinitely massless rod. There's just a point particle at the end of it. That would be mh squared or mr squared. And it's not a sphere either. It's not a cylinder. It's nothing like that. It's more like a cylinder, but a very crunched up cylinder called a disk. They want us to model the merry-go-round as a disk. The eye of the merry-go-round is 1/2 mr squared according to what's in the book. And again, there's derivations of this. I think I gave derivation of that as well, you guys. We don't need to really explore that right now. Just know this. I mean, for right now, it's 1/2 mr squared is the moment of inertia of the merry-go-round. Though that is not an obvious assumption to make, that's the assumption that's being made, guys. We will know that each kid now is on opposite ends of each other, diametrically opposed. So they are each a radius away from the center. They are a distance, the radius away from the center. So I am IMGR plus one of the children and then the other child. They have the same mass, so we can model it like that. I equals 1/2 mr squared. We talked about that. They use capital R. I use small r when I've done these, you guys. Here we go again. I got a capital R and small r are equal. So they kind of get used interchangeably. We're not going to nickel and dime it over semantics, guys. Okay. The kids are R away, so they're capital R away. M capital R squared plus M capital R squared. MR squared plus MR squared is 2MR squared. Okay. This is the mass of the merry-go-round, capital M. Small m is for the children, but they're a radius away. I wrote it a little bit differently in my notes. I used small r. If I change it back to small r, you're really going to want to punch me in the face, I think. So what do we got here, man? How does this whole thing play out? A half is a half. M is 180 kilograms. The radius is 1.5 meters. So if you take the radius 1.5 meters and square it, you get 2.25. 2.25 is the same as 9/4. 9/4 times 180 is going to be, why did I get myself into this? Is going to be 405. Half of 405 is 202.5. The kids are each 30 kilograms. 2 times 30 is 60. 60 times the quantity 1.5 squared, 60 times 2.5 is going to be, let me try that one as well, guys, 135. So 135 plus 202.5 is 437.5, something like that. And there it is. Yeah. So plug in the numbers, guys. Grind this out. 337.5 kilograms meters squared. That is the I. If they ever asked you that, then here's the answer. If they ask you that, then there's the answer. Let's see what else they're saying. They're going a little bit further. For A, they're saying, please tell me what the moment of inertia is. So a number of ways to go here, guys, I guess you could say. Let's be careful how you want to play this game, I guess. 53A, L is equal to I omega. So find the magnitude. We said the radian is kind of the lingua franca when you're doing a lot of this stuff in terms of much of the classic mathematics. All this stuff gets proved vis-a-vis radians. I said the Taylor's great theorem. The Taylor theorem and some of the great applications of Taylor's theorem, when they're doing the trigonometric functions, they're going to work with radians. You can actually I can make Taylor's theorem work for anything as long as the angles are valid. It's just it's substantially more complicated. It's somewhat more complicated at the least. Okay, that's not our business. Your best deal on this to really make this under control, work real good, is go for the radian. Do you understand that they are telling us it's one revolution? It's a half a revolution per second. Let's see here, it's 0.5 revolutions per second. Is it true that omega is 0.5 revolutions per second times 2 pi radians per one revolution, for every revolution? These are seconds. 0.5 times 2 pi is pi. It's pi radians per second. That's omega, ladies and gentlemen. That's omega. We already know what I is. It's right there. The rest is pretty straightforward stuff. The I is 337.5. 337.5 kilograms meters squared times omega. That's it. Work that thing out and you're in business. You're in business. We got 1060.3 kilograms meters squared per second. Yeah, it looks kind of bizarre, but that's how you do L. That's the L. That's what L equals. The radian guarantees that you're going to keep the units that you want to keep. Everything that I've been doing is kilograms, meters, seconds, MKS system of units. The radian guarantees you keep it if you already have it present. Very important. What is the kinetic energy of the system? Well, look, guys, let's get something straight. That merry-go-round is not moving from, that merry-go-round is not flying around the park. It's not driving, it's not being driven from Milwaukee to Chicago, or from New York to Washington, D.C. or something. It's staying right there. The only consideration for kinetic energy is rotational kinetic energy. So, for B, okay, we know that. We know this. We've been there. The hardest part of doing this stuff is just sitting down and doing it. At first glance, we already know where we're going to go. We're going 1/2 I omega squared. That's 337.5. What's omega? Yeah, well, here's omega. It's pi. It's pi. Omega's pi. So we're going to square pi. Squaring pi is about 10. This thing's going to be, about half of this is, 1670, about 1700 thereabouts or whatever. Okay, grind this thing out, guys. Let's see what we got here. The KE at the end of the day is 1,665.5. That's it. Now what? Well, for C, you guys, they are telling us, for C, they're telling us what happens. Again, there appears to be a wrong answer in the answer key in the book. So I'm probably going to stick with the answer I'm going to give you right here. Let's just take a look at what's going on here, in case I missed something. But I got a feeling. Well, I got a feeling I did not. But but that doesn't mean anything. I mean, I easily can be wrong. I'm wrong a lot. So let's look at it. While we're doing this live, I guess, or at least I'm filming this live right here. Let's see where we are. Let's see what considerations you want to bring into play here. If you agree with what I'm saying here, or if you're going to agree with the book. Now, this one's 53. The odd number should be in the back of the book. They want to know what happens when the kids walk toward each other. Now, let me just, I want to make sure I'm doing it because I don't want to call these people wrong just yet. But there's two children, the merry-go-round, the mass of the merry-go-round, merry-go-round is spinning, we got all that, calculate the angular momentum. Radius is this. Both children walk half the distance toward the center of the merry-go-round. Unless they meant something different, guys, I think they might have done this wrong. Both children walk half the distance toward the center of the merry-go-round. So both of them are about to meet, going toward the center, but not making it toward the center. One guy's 1.5 meters away from the center, the other guy's 1.5 meters away from the center, and then they both walk toward the center, halfway to the center. So from 1.5 meters, they go to 0.75 meters for one guy, and from 1.5 meters goes to 0.75 meters for the other guy. That's the way I took it. Perhaps something else was meant, or perhaps they simply made a mistake. We all make mistakes sometimes. That's not a big deal. Actually, it is significant. We make mistakes sometimes, but mistakes are mistakes. But if these guys are doing thousands of problems like this, guys, I guess it's understandable they're going to make a mistake sometimes. We're all going to do that sometimes. Momentum is conserved. What does that mean? That means angular momentum is conserved. Angular momentum is conserved. Regular momentum is conserved. Translational momentum is conserved. Angular momentum is conserved, and energy is conserved. So those are universal laws of nature. From the very, very huge masses and circumstances that exist in the universe to the most minute. For all that they know, momentum, both linear and angular, is always conserved. Energy is always conserved. I will say this. There's an initial system. There's an initial situation, I omega. And there's a final situation, I omega. And that's about it. That's about how we're going to do it. Omega sub f equals omega sub I over omega sub f times omega sub I. Yeah, I agree. Great, let's talk about it. What was the initial circumstance? The initial circumstance is 1/2. Again, I used small r when I did this. Remember, guys, it doesn't matter small r or big R. I said small r equals big R. So let me go to small r again. So it looks like the notes I got in Canvas, but that's so okay. Small r and big R are the same thing. Okay. Big M is the mass of the merry-go-round. Small m is the mass of each child. What's going on now? Well, it's the same merry-go-round, you guys. That hasn't changed. Yeah, the kids are going different. The kids are somewhere else, though. Each child is r over 2. Is at a distance of r over 2 now. And that's omega sub I right here. That's it. This is kind of the premise of the whole thing, you guys. If we're going to do this, I think this is the premise of the whole thing, you guys. To make it happen. What we do here, let me see it. Let's see what I can say here. Let me verify it in case, because I think they gave something different. There's no two ways about it. Well, the top part, we already knew what it was. That wasn't really an issue. We already derived that one. We already know what that one is. Omega sub I was pi, right? Pi radians per second, 3.1416, thereabouts. This guy right here is a little on the rough side. You got to watch out what the heck's going on this one. We said this came out to 202.5. This times 30 is 60. This is 1.5 divided by 2 is 0.75. That's 3/4. 0.75 is 3/4. If you square it, you get 9/16. 9/16 times 60 is 500. 9/16 times 60 is 540 divided by 16. So let's see what the heck that would be. Let's do a couple of division. That'd be 270 divided by 8. That'd be 135 divided by 4. That'd be 62.5 divided by 2, and that'd be 31.25. So 31.25 plus 202.5 is 233.75. I'm wondering if I wonder if I did something wrong here. Maybe we're catching something here. Let's see. Let me see. Let me just. I want to make sure I'm doing this right, guys. I got a feeling the number I put on the bottom here in my own notes might be off, but I wouldn't be surprised if I did that one wrong. Let's have a look here, guys. Let me start this thing from scratch, just for the heck of it, guys. Right, 202.5. I got that right. No, it's spot on, guys. What I did in my mind was off. Right. I mean, it's basically this. It'd be yeah, it's right. It's what I had actually done here was right. Let me initially at least 9/16. That's 540/16. That's 270 over 8. That's 135 over 4. That's 67.5 over 2. And then that's 33.75. 33.75 plus 202.5 is 236.25. Yeah, okay. I just had done the mental math wrong, guys, but everything else is, yeah, it's spot on. I'm trying to find some way that I'm wrong or perhaps they're wrong. They appear, indeed, in the final analysis, it seems that the answer they're giving is not quite, the answer that they're giving is not quite right. If you take this one and take it and see where you're going to go. Now, again, we found omega sub f to be 4.49. Yeah, I know. What was it initially? Well, it was pi. It was 3.14, 3.142. 3.142 radians per second. 3.142 radians per second compared to 4.49 radians per second. Of course, when the kids get closer to the center, the moment of inertia, the moment of inertia changes, gets smaller, so they're going to rotate faster. Momentum is conserved, and you got what you got. So yeah, this is where it's at. I will stay with this answer. The answer key appears to be wrong here. When they said that, what the heck? We got this far. Let's look at 53 in the answer key. They said 4.9. Yeah, it's the answer they're giving in the end. They're giving a little bit different answers than I'm giving here. For 53, they're making the claim it's 4.9 radians per second. I don't agree. Something got messed up here. The 4 and the 9, somebody must have just truncated the 4 and made it 4.9. It's easy to copy something like this wrong, I guess. I'm staying with that. They appear to be wrong when they did that. All right, guys. That is 53. Let's look at 54. Okay. For 54, 54, they're saying a disk of mass, M1, is rotating freely with constant angular speed omega. Another disk of mass M2 that has the same radius is gently placed on the first disk. If the disk, so I'm assuming the other one's not rotating, you guys. They didn't say that the other guy is rotating, just one of them is rotating. They didn't mention rotation for the other one. So again, you got to make some assumptions here. A disk of mass M1 is rotating freely with constant angular speed omega. Another disk of mass M2 that has the same radius is gently placed on the first disk. If the surfaces in contact are rough so that there's no slipping between the disks, what is the fractional decrease in the kinetic energy of the system? Okay, so they want you to kind of figure out when it's doing this. Let's play some mathematics and find what we can say. Okay. So they're staying with a lot of symbolism here, guys, and that's fine by us, I guess. We can do it. For 54, it's looking like that. Let's just keep it like this for now, maybe a little easier to look at. There is a lot you can say, I guess. They kind of call it omega. I'm going to call omega. Omega is the first disk. It's angular velocity. Angular velocity, the magnitude of the angular velocity of the first disk is omega. I'll call that first disk omega 1I. 0 is omega 2I. Omega F equals angular velocity of two together. So this is the final All right, there's a lot going on here, I guess. The I of any disk, assuming uniformity and the mathematics is all going to be well behaved for us, assuming we got uniformity here, we're talking about 1/2 mr squared. I think they said they were the same radii. Some of these problems are so convoluted, it's hard to remember what you've read, I guess, but what are they saying here? That has the same radius. That has the same radius is gently placed on that one. Okay, sounds good to me. There it is. It's all there. Now what? Well, we got stuff on here, guys. We see what we got. We got all this. Let's see what we can say. Let's say this, guys. Let's make life easy. Moment of inertia of the first disk with its angular velocity, multiply the two, you got angular momentum. Angular momentum is conserved. This is what's going to get us there. Moment of inertia times omega will give me the angular momentum. So angular momentum and angular momentum initial equals angular momentum final. Angular momentum is conserved. Let me take these two and put them together. And then when they merge, there's an omega sub f. So we're here. We got something like this. So let's see what we got here. Well, initially, that guy ain't rotating. He's 0. 0 times this is 0. You just got this guy equals that guy, which means what? Which means I1 omega 1I equals I1 plus I2 omega F. We want to find, I think we want to find the omega, I think we're talking about kinetic energy and everything else. There's a lot going on here. I'll tell you what we're going to do. This guy is 1/2 mr squared. So I don't know, guys. You see the capital M and the small m. Capital M and small m get used interchangeably, so do the R's. Forgive me, the way I wrote this here, I kept it like this. Let's keep it like that. Doesn't matter. The capital M and the small m are the same. The big M and the small r. The capital M and the big M are capital M and small m are the same. Capital R and small r are the same. So let's go here. We got 1/2 M1, let's just use what they told us, or some measure of it. We got this, times omega 1I, which is just this guy. This guy right here is this. And this right here is 1/2 M1, 1/2 M1 R squared plus 1/2 M2 R squared for the other guy. So all this is going to be that. So you got that. Okay, great. Is there an easier way to write that? Yeah, there's a lot easier way to write it, or at least somewhat easier way to write it, I guess you could say. 1/2 M1 R squared omega equals 1/2 R squared, 1/2 R squared. You got the omega F here. I'll tell you what I can do. This M2 and this M1 well, let's do the math. Sounds good to me. Any ideas? Yeah, we need some ideas here. I mean, what we're going to do is we're going to take omega sub f all by itself. We're going to multiply both sides of the equation by 2 and divide by the quantity m1 plus m2 times r squared. So what we get here is m1 r squared omega. We're going to multiply by 2 on each side, divide by all the rest, leave omega sub f by itself. This and this. Yeah, that's a true story. This is what I need. Because now I'm going to compare kinetic energies. I want to see the amount of kinetic energy that's lost. My assumption is kinetic energy is going to get, maybe it won't be. I have to see. I'll see what kind of numbers we get here. My assumption is to find out what's going on here. I got to go delta KE. I got to see the loss of kinetic energy. The loss of kinetic energy over KEI, which is the same as KEI minus. We're working under the assumption, it'll come out. It'll come out. We're working under the assumption that the initial kinetic energy is greater than the final kinetic energy. Some kinetic energy was lost. Well, how was it lost? Well, I mean, it's lost. There was a big amount of kinetic energy, and now there's a small amount of kinetic energy. So they're sort of tipping us off. That's not enough to be drawing too many conclusions, guys. But let's draw that conclusion for now, and let's see how it goes. But let's see. Let's see what this means. KEI goes into KEI one time. Minus KEF over KEI. This is it. This is what we got. We got to work with this and figure out what we're doing. All right, let's go. Here's one. KEI is 1/2 I omega squared. So let's see what we can do here. Okay, we'll go a couple ways here, I guess, to do this. I just don't want to be too quick on this and kind of not make some sense out of it at the end of it. All right, we've said a lot. We've got more to say, and we're going to say it. We are in a situation where, let me sort of argue with this thing a little bit here. Let me write a little different from the notes, guys. Look, what's KEF? The final kinetic energy of the system, is 1/2 times the quantity I sub 1 plus I sub 2 omega sub F squared. KEI is 1/2 I 1 omega squared. Sure don't look like that's a lot. This doesn't look like it's bigger than that, but let's find out. Let's find out. That's where it's going. That's where it's going. Guys, did we discover what omega sub F was? Yeah, we sure did. Remember that. Because I'm going to put omega sub F right here. Then I'm going to square it. Is it true that I1 is 1/2 m r squared? Is it true that I1 plus I2 is 1/2 m1 plus m2 r squared? Yeah, that's true. The delta KE over KE initial is going to be 1 minus one half m1 plus m2 r squared times omega sub F squared. Don't forget that. The other one is 1/2 m1 r squared omega. You guys with me? The halves cancel. The r squareds cancel. Forgive me for going backwards here, guys, on this whole thing, but we got delta KE one minus M1 plus M2 omega F squared. Yeah, here's omega F. Let's get down to business. That's squared. Right? Wish I had more room, guys. Sometimes depends where you want to write now. That guy's squared. Over. Time out. That should have been squared right here, right? Right, it was squared over here. We got 1/2 M1 r squared omega squared. So this has got it. That's squared, and that's got to be squared. Okay. Okay, it's still a mess. What's going on here? Well, that's M1 squared over the quantity M1 plus M2 squared times omega squared. The quantity M1 plus M2 cancels into the quantity M1 plus M2 squared. So it's going to be M1 squared over M1 plus M2. Looking good. Yeah, it's all right. We're just not doing anything careless here. This is usually, and I said not do anything careless, and I already did, right? Okay, here's 1 minus all that. Minus all that. M1 omega squared. That's gone. That's gone. M1 goes into here. M1 goes into M1 squared, just M1 times. This is pretty fascinating stuff if you're really careful about it, guys. 1 is 1 minus a fraction. What kind of fraction are we talking about? You're talking about a fraction of the masses. Kilograms divided by kilograms is unitless. It's got to be unitless, guys. It's got to be unitless. Yeah, that's a true story. That's definitely a true story. You're going to hate me for it, but there's another way to write it. Is 1 the same as M1 plus M2 over M1 plus M2? Is 1 the same as M1 plus M2 over M1 plus M2? And this is M1 over M1 plus M2. Wait a minute, you got a common denominator, subtract the tops. What's M1 plus M2? What's M1 plus M2 minus M1? It's just M2. It's a little easier, guys. the aesthetics are better if you write this. There's nothing wrong with this. This is true. There's just a better way to write it. And the better, I mean, I don't know, you can argue how much better it is, but you got delta KE equals KEI minus KEF over KEI. And man, yeah, you got it. I mean, you got it. It's M2 That's true, certainly true, but this is better. Better in the sense, I don't know, I'm not even sure it's better, guys. They're both true. Depends how they're asking you to write the answer, I guess. If it was a multiple choice type question and this was the only one offered, this was the only correct answer that was offered, this is definitely a correct answer. A bit convoluted, but it is correct. It's mathematically correct. That's definitely mathematically correct. This is cleaner. This is a little bit of a cleaner look at it. Again, you got it in the notes. You see how I got that done on the notes as well, guys. That's 54. Let's do 70 and 71, and we'll call it. For problem 70, it's kind of a long one. I mean, a pretty long problem, but we'll figure it out. I got it done in the notes pretty well. For problem 70, a ball of mass capital M is 5 kilograms, and radius small r is 5 centimeters, is attached to one end of a thin cylindrical rod of length capital L equals 15 centimeters, and the mass M is 0.600 kilograms. The ball and rod, initially at rest in a vertical position and free to rotate around the axis shown, are nudged into motion. A, B, C, D on this one, guys. A, what is the rotational kinetic energy of the system when the ball and rod reach a horizontal position? B, what is the angular speed of the ball and rod when they reach the horizontal position? C, what is the linear speed of the center of mass of the ball when the ball and rod reach a horizontal position? D, what is the ratio of the speed found in part C? Let me just see here, guys. What is the ratio of the speed found in part C to the speed of the ball that falls freely from the same distance? If it were to fall free fall. Okay, there is a lot there. Let me make some sense out of it, I hope. All right, well, conservation of energy considerations. I remember a while ago, problem similar to this, we had tried to do. An acquaintance and I had looked at it, and we had looked at it outside of energy considerations, and it was quite a difficult situation to deal with. Probably manageable, probably could have been done, but we ran into some roadblocks when we were doing it. Your best way is to look at energy considerations when you're doing this whole thing. They're essentially telling you about all this is quote-unquote well-behaved, I guess you could say, as a system here. And you're allowed to make some assumptions that make this a lot easier to deal with. If you've got this thing right here, you got this right here, and you're pivoting it right here, and you're going up here, and it's the rod itself, here's mass M, small m for the rod, big M for the sphere. To get up to here is capital L, and this right here is the diameter, D, and it may not, and that's the center of mass right there for that, and so that'd be D over 2. You know, and it's, the thing's being thrown downward, or just nudged, actually not being thrown, sorry, nudged downward. What happens when it's right here? You know, how fast is it going when it gets down to here, the horizontal? How does that compare that if you had the ball not attached to the rod, the ball was by itself and you dropped it, how would its speed compare that way if it was just dropped that way? They're going along those lines when they're saying this stuff. So they're going A, B, C, D. It's a whole alphabet here, guys. There's a lot you can say, and they'll let you get away with some stuff. Let me get away with it. Let me use the out that they gave me. You know, are they going to make you do something like this? If they do, they're going to tell you a lot of the outs that you have to get out of something when you're doing something like this. Okay. Let's start moving this thing and see what we can do. We've got this right here. You know the deal on this stuff, guys. You've been there. You've seen this stuff. Potential energy plus kinetic energy initial equals potential energy plus kinetic energy final. The initial potential energy of the system, and it's a little messy here. Well, first of all, let's make it easy. The initial kinetic energy of the system is 0. It just got nudged. Didn't really have any kinetic energy to speak of. So then you got this guy is equal to kinetic energy final. Final's down here. Final's down here somewhere. Kinetic energy final, and that equals, and that's it. Forgive me. There's no potential energy at the very, for our purposes, there's no potential energy at the very bottom, and there's no kinetic energy at the very top. So PEI equals KEF, and all right, sounds good to me. That's going to be the final kinetic energy then. How about mass? Now we got to be careful here. This is the mass of the rod. We're going to be very careful here. The mass of the rod, I'll say M sub r. That doesn't mean multiply by r. It's M sub r for rod. G is G, and Y is the center of mass of the rod. We'll get to that in a second. The ball. Mass of the ball times G times Y, the H, the Y of the center of mass of the ball. Let's talk. Let's talk. I don't like the way I did it in my notes, to be honest with you. So I like some parts of it, but all right, we can look at it. The rod is mass M. Its center of mass is L divided by 2. We'll talk about that. So The mass of the ball is capital M. Its center of mass, now I got to be careful how they did this. The mass of the ball is 5 kilograms. So capital M is 5 kilograms. The radius of the ball is 5 centimeters. 0.05 meters. The length of the rod, is 15 centimeters. Length of the rod is 15 centimeters. Its mass is 0.6 kilograms. Okay, maybe that. There's a lot of ways I want to go here. I'm just a little apprehensive of going too fast regarding some of this stuff. All right, what's going on here? L over 2 is the location of the center of mass of the rod. M times G times this. M times G times half the length of the rod is the height of the center of mass of the rod. This guy right here is kind of, where's he located? Well, he's located at a height of, well, let's talk about a few things here, guys, if you don't mind. This is G, and this is L plus R. I think I wrote it a little differently. That's neither here nor there. That's it. That's where you want to go. The potential energy equals the kinetic energy final. The initial potential energy equals the kinetic energy final is equal to this song and dance right here, guys. What happened? There's a lot that happened, I guess you could say. I mean, so you got this. The whole thing is this guy equals all this. Well, how does that work? Well, you could factor a G out. You could factor a G out of there and just go. You could factor a G out of here and then go for it. 0.6 times half of 15 centimeters is 7.5 centimeters, which is that many meters. I want to stay with meters. 5 kilogram ball, 15 centimeters, 15 centimeters to get up to here, another 5 centimeters to get up to here. That's 20 centimeters. Times G. And there it is. For A, we got, grind that thing out, you got it to here. That's that. The answer key for Dr. Katz's book treats the ball as a point mass. So if you're going to treat it as a point mass, you can find what the omega is going to be at the end. You could say, okay, 1/2 I omega squared at the end of that whole thing. So 1/2 I omega squared equals 10.25 joules. True. It treats it like a point mass, so you better be careful. You better be really careful. Treats it like a point mass. Treats it like a point mass, huh? All right, if that's the case, then let's be careful. Let's use this. Let's find what the moment of inertia is of the rod. The rods of length L, we're finding the moment of inertia down here. I guess we'd have to look that up. And looking that up, we get 1/2 mass of the rod times the length of the rod squared. Plus the large mass, the ball, h squared. And h squared, we'll talk. Yeah, that's true. We're not going to use the parallel axis theorem and go, hey, wow, 2/5 mr squared is the moment of inertia of the ball about its center of mass plus mh squared. You're not going to go the 2/5 mr squared for the moment of inertia of a sphere. You're going to just go, the sphere is a point mass. We're not going to use 2/5 mr squared. We're just going to use the sphere as a point mass and move it a distance h from here all the way to here. What is that? That's L plus half of D, which is R. That's L plus R. So that right there, you guys, that H is going to be L plus R. So what happens is, what happens is what we're going to do. We're just going to figure it out then from there. We're going to say, okay, what's going on? This is it. Just remember it means this. That's very, very important, guys. And this is going to get us out of a lot of things. It is, if I only knew how to write, let me see here, guys. It's good to catch this stuff now rather than later. It's going to be omega sub f. It's going to be one half. The I is all of this. And the omega squared is omega sub f squared is equal to 10.25. All right, guys, that's better. Let's find what omega sub f is. Let's find what omega sub f. I said omega in my notes. Omega sub f. It's a horse apiece, guys. Let's make a long story short, I guess you could say. To find what omega sub f is, which is omega the way I got it written, the quantity omega sub f squared, go the whole mess here, I guess, go 10.25 take the half in there. This whole thing's, remember now, you got to go half all the way in there. This is 1/6 small m L squared plus 1/2 etc., etc. Basically, guys, what are you doing? What are we doing? This is 0.6 kilograms. This is 0.15 meters. This is 0.6 kilograms. This is 0.6 kilograms. This is 0.15 meters. You're going to square the 0.15 meters. That's a sixth. That's a half. This thing right here is going to be 5 kilograms. This is the 15 centimeters plus the 5 centimeters for the radius. 15 plus 5 is 20 centimeters. That's 0.2, the quantity squared. You got all this. Go for it. Make the whole thing work, you guys. And the answer key for Dr. Katz's book, like I said, treats the ball as a point mass. You don't have to, but she says it's okay. I mean, it's probably a good assumption. At the end of the day, you guys, I know I wrote omega, in my notes I wrote omega. I meant omega sub f at the very bottom. And it comes out nice. Comes out nicely, I guess you could say. And there it is. And that's for B. Dr. Katz informs us that this is a good approximation. Let's be more precise and confirm this. For the record, let's find omega more precisely and see that our approximation of omega is 10 radians per second is quite good. And what I did right there, guys, was I'll leave it for you to look at it in the notes. But you'll see it in Canvas. I simply left everything just like this. I left everything just like this, you guys. I left everything just like this, but then I put inside of here plus 2/5 mr squared in addition to all that. So you got bring this guy in there, bring this guy in there, and bring that guy in there and see what happens. Do that. Plug that in there. Just plug. That's all I did. I just put it in there just now. You didn't have to put it in there. But again, let's just confirm Dr. Katz was it. What I did was, now I used the parallel axis theorem, ladies and gentlemen. Now I took mh squared and then 2/5 mr squared from the parallel axis theorem. Now I'm putting it in there. Work it, you guys. You get omega is 9.9 radians per second. So omega equals 10 radians per second is a decent approximation. It's a decent. You get 9.9. Why are you going to get a smaller answer, you guys? That much we know. That much we know. Why are you going to get a smaller approximation? Because this guy right here, this whole matter right here, you just put something in here that wasn't in there before. When you divide by this, it's a bigger thing on the bottom. It's 2/5 mr squared. There it is. I mean, like that. I just changed it. Say, okay, now do it. Well, this is a bigger number. This makes the denominator bigger. Divide this by something bigger than what it was before, you get a smaller answer. The square root's going to be a smaller answer than the square root was. That's why you get 9.9. See what they're saying here. That's A and B. Okay, you see all this stuff, you got it. Let me erase what I need to erase, I guess you could say, and we'll take it from there. So we're saying a bunch of stuff here. Still on this problem. We did A and B, now we got to do C and D. As I said, the whole alphabet's on this one, guys. It's kind of the problem that doesn't end, but I think we did the bulk of it just now. The bulk of it right now, I think, makes us look pretty good. We're in pretty good shape when we do this. Okay, so C is saying What is the linear speed of the center of mass of the ball when the ball and rod reach a horizontal position? Okay, that's pretty easy. That's pretty easy. How does that work? You guys already know. You guys already know that V is omega times R. Big R, small r, whatever you want to call it. What are we talking about? What is the linear speed of the center of mass of the ball? Well, the rod is length L. The radius is small r. That's what this capital R is going to be, that guy. And omega is omega. V is going to be omega times big R, some big R. Well, what's the center of mass of the ball? We said it's going at 10 radians per second. This is 20 centimeters, which is 0.20. This is 0.20 meters. This is 10 radians per second. 10 radians per second times 0.2 meters. That's the end of the story, you guys. How fast is that thing going? The center of mass is going that fast. It's that simple. If you use omega is 9.9, if you use omega is 9.9, then it'll be 1.98. Still pretty close. Not bad. But still, I mean, there's some subtlety here. And I talk about that in the notes. Can you tell me, how does that speed right there, guys, compare, what if that ball went free fall from center of mass to that position? From 5 centimeters plus 15 centimeters, 5 centimeters plus 15 centimeters, it fell 20 centimeters. How fast is it going? That's interesting. Well, let's play a couple games here, I guess you could say. Everybody's falling down, so we're not going to worry too much. Is it okay to figure out what we're going to do here? Initially, it ain't moving. Finally, it's got some speed. So D is VF squared over 2A. Yeah, the A, since everybody's falling down, we can call everybody positive. Be careful. We can call everybody positive, though. If not, you can call it negative, and negative here, but that's going to be negative, and it's going to be just the same. Actually, be careful on that. There's more to that. Let's not go down this path too much, guys. There's ways we can walk around it, but let's not even go here. What do you say? You multiply by 2g on each side. D is the same as h, height. Interesting. 2 is 2. G is 9.81. H is the height of the center of mass, which is 15 centimeters plus 5 centimeters, because the radius is 5. That gets me to the center of mass. 5 centimeters plus 15 centimeters is 20 centimeters. That's 0.2 meters. Two times 9.81 times. How does that compare to 2 meters per second, or 1.98 meters per second? Pretty fascinating stuff. At the end of the day, that's 1.98 meters per second. And you know what? And it's not a slam on anybody writing the book. They wrote a great book. Brilliant stuff here. Brilliant people doing this kind of stuff, guys. They know much more than I do. I guess we should have, just to kind of play it safe. Remember, strictly speaking, the thing was 1.98 here. Remember, when we plugged in the 9.9, we got the 1.98. They're the same, you guys. How do they compare? The ratio is 1 to 1. They are the same. They are the same. They're essentially the same. In other words, if this ball falls straight, no air resistance, no anything. If this ball falls straight down and it fell 0.20 meters, if it fell 0.20 meters straight down, at the end of that journey, 0.20 meters straight down. It is going in that free fall that took place at the end of the 0.20 meters fall. It's going 1.8 meters per second. It's going 1.8. It's going 1.98. It's going 1.98 meters per second if it free falls down. If it free falls down, but on a lever arm, at the bottom, it's still going to be going the same speed. Pretty fascinating. Pretty fascinating. The conservation of energy guarantees that, in a sense. Assuming no friction present, no air resistance present. There is potential energy on the top. At the bottom, all of that potential energy is going to be brought down. All that potential energy is going to be manifested in kinetic energy. And as the circumstances are, it'll come out this way. If it's a point mass, it's a little different dynamic. I guess this accounts for it. This is truly remarkable in that regard, how that works out. When you account for the parallel axis theorem, it's exactly the same answer. Okay. All right, guys, let's talk about 71. Again, chapter 13, the Katz book. Problem number 71. A long, thin rod of mass equals 5 kilograms and length equals 1.2 meters rotates around an axis perpendicular to the rod. With an angular speed of 3.00 radians per second. A and B here. What is the angular momentum of the rod if the axis passes through the rod? If the axis passes through the rod's midpoint. What is the angular momentum of the rod if the axis passes through a point halfway between its midpoint and its end? So it's two different scenarios here for A and B. The way some of this stuff gets mentioned, guys, sometimes can be a little messy. For A, I think they're going, here it is. And, okay, I'm not sure of a good way to write this, and I just managed to mess it up. There's a number of ways you could look at this, but here's the rod, and it goes around there, and it goes around that. So that's one scenario. The other scenario, here's where it would have been. This is right through the center of mass. What they're trying to say without really saying it is, in the first scenario, it is rotating about an axis through the center of mass. It's rotating about an axis, I can't even talk. It's rotating about an axis through the center of mass. That's that scenario. The other one, it's rotating not here, but here, which is halfway through there. And it's around here that it's going for two matters there. What's the angular, what are the angular momentum of the rod if the axis passes through here and, et cetera, et cetera. Okay. Well, for the first scenario, when you're going through the center of mass, the moment of inertia for the rod is 1/12 ml squared. And the thing is length L. And that's it. That's I. So L would be I omega. That would be 1/12 m L squared omega. That would be, here we go, 1/12. The mass of the rod is 5 kilograms. The length of the rod is 1.2 kilograms. You can square it. You can take all that, you're going to multiply it by omega, and omega is 3 radians per second. Let's see what we got here. Right. Now again, they're keeping it here at 3 radians per second. They don't explicitly say it, but I think we got to kind of assume that when we play the game here, guys. So this is the way it goes. There's a lot of ways to look at this. We kind of there's like a shortcut here to it, and I don't want to make it too much of a. That's 1/10. That's a half. 1/10. That's a half. That's 0.6. I got 1.8. Yeah, it's 1.8. 1.8 kilograms. Look, you don't have to try to do the mental gymnastics that I'm doing here. So I give myself a boost of confidence. I can do the mental math still, I guess. Bottom line is you got the calculators. You go about any way you want. Let's get the right answer at the end of the day. Let's be looking at this thing and let's get the right answer when we're doing it. Period. It's the end of the story on that one. What we can say here is for the other one now. That's A. This is B. If this is... Now we've moved this guy. What's going on here? What's going on here? Guys, the center of mass of the rod is here. You have moved the axis. You've moved the axis away from the center of... This is the center of mass of the rod. You've moved the axis over here, a distance h. You know that I is going to be ICM plus MH squared. We know that. So what do we have here? Well, I know this much. I mean, I is I. The I is going to be something, and that's going to be 1/12 ml squared. 1/12 ml squared. I got that. What's the h squared? It's halfway between the end and the midpoint. Well, if the whole thing is L, that right there is L over 2, and that means that this right here is L over 4. If the whole thing right here, if this whole thing is L over 2, half of that is L over 4. It's pretty neat. Yeah, absolutely. A lot of ways to go. Look, there are a lot of ways to go. They're all easy. It depends how how rigorous you want to get in your manipulations of what's going on here, you guys. You know, you could take this and say that I is equal to 1/12 ml squared plus 1/16 ml squared. If I add those, wow, you need a common denominator. It can get kind of messy, but this could be 4/48. This could be 3/48. So you can go here. L is going to be the I, which is 7/48. You don't have to do it this way, but the mass was what they say. The mass was 5. Mass was 5. The length was 1.2. Length was 1.2 squared. And omega was 3. I'm tempted to try to do this in my head too, man, but let's see where it goes. Let me try to think about it. There's a way you could play a game here. You can go 5 times one of these 1.2s. 5 times 1.2 is 6. 6 goes into here 8 times. So it's 7/6. I'm sorry, 7/8 rather. I mean, so if this was 5 times one of the 1.2s, it'd be 6. 6 goes into there. 6 goes into here 8 times, so it's 7/8 times 1.2 times 3. Well, okay, 7/8 times 1.2. 7 times 1.2 is 8.4. Times 3 is 25.2. 25.2 divided by 8 is 3 and 1.2/8. And from there, you know, 3 and 1.2/8, how is that all going to play out? And we can figure out where that's going to go. So 3 and 1.2/8, that's the same as 6/40, which is, you know, 0.15. I mean, so I'm 3.15. I'm throwing that out there right now. I'm probably wrong, but let me turn it and let's see. 3.15. Okay, I lucked out on that one. All right, so you look at it, guys. Look, you don't need, again, I'll try to not get into the habit of doing this too much. Sometimes it goes faster that way. Other times it's people wondering, what am I doing? But when you get to here, the 3.15 is definitely the answer. So 3.15 kilograms meters squared per second. .15 kilograms meters per second. That is it. It's a neat chapter. I mean, we'll see how we can proceed with this stuff. We've got time constraints. It takes a long time sometimes in some of these guys, but go at the pace you want to go, and hopefully this stuff helps you out a little bit. I will talk to you guys soon. right, guys, something got a little mixed up, but let's see how this works out. Okay, I'll see you guys later. Take care.